Congestion management, the concepts and design. Well, we've finally come to the point in the Quality of Service series where we can take those classifications and markings that we've been applying to our packets and do something with them. Right now we have these boxes going through our networks or packets that have the markings on them, but the router's not treating them any differently. The first set of tools I'd like to show you is the most well-known tools that people can use to manage their traffic congestion. They're the queuing methods that Cisco has deployed. The first section I want to go through is understanding those legacy queuing methods. Now I know some of you might be thinking, well, why do I want to understand the old world when we have all these new queuing methods that I've heard about? Well, the reason why is if you understand the old world, you already understand the new world. Here's the funny thing. You see that second bullet on there. It says the new, not so new methods. The new methods that Cisco has deployed is just compilations of the old methods. And I'll talk more about that as we get into it, how they took the old pieces and assembled them together into this fancy new queuing method that just about everybody's heard about called low latency queuing, or LLQ. And finally, we'll go into bandwidth provisioning, because we're going to find ways, as we go through this, of carving up our interface bandwidth into specific sections. If you're not careful, you may carve it up too much, to the point where your network doesn't work the way it should. That's going into the design and the planning of quality of service and provisioning your bandwidth correctly. First in, first out, or FIFO queuing, is one of the easiest queuing methods to understand, because it really makes sense with how packets are received by the router. It's like a line of people that are standing in line for tickets or a concert or a movie. The first one to get in the line will be the first one to get served, and the last one to get in line is the last one to get served. Just like that, your router is going to be receiving packets in a steady stream. The first packet to get there will be the first one to be sent, and down the line we go. The problem with FIFO is that it's sometimes a little bit too fair, in the sense that the first one to get there is the first one to get out, but the first one is not usually the packet that we most want to get out. For example, a bandwidth-hungry data application may be sending thousands of large packets, but we want some of our small voice packets to be sent first. In that case, this method is not the best way to go. A lot of people will accurately refer to this as a best effort delivery system. The router's going to try its best to get there, but if not, oh well. Tail drop will occur, and the last one that's standing in line will end up being dropped and having to be retransmitted. With FIFO, you have one queue available to you. One queue that's being received and one queue that's being sent for the traffic that's going through your router. The method of queuing that it's using is first in, first out, just like I described. There's no delay guarantee, there's no bandwidth guarantee, and of course this one is not recommended for voice. So the demand was born. People said, we need more than best effort. We need to be able to give things priority. And that's where priority queuing came from. Priority queuing is a little bit overkill, and that's how it got the nickname brutal queuing, and here's why. It's a lot like buying a lawnmower, or maybe 1,000 lawnmowers. You want to get 1,000 of them for your friends, family, and neighborhood, and anyone else who needs a lawnmower. And there's 4 stores that are selling lawnmowers. Maybe there's a Walmart, Target, Radio Shack, Special Delivery, and Lowe's. You have these 4 different stores, and Walmart has them for $10, Target for $100, Radio Shack for $1,000, and Lowe's, yeah, they're at $10,000 for a lawnmower. So where are you going to go first? Well, you're going to go to Walmart, and you're going to buy as many lawnmowers as possible from Walmart. So say you get 100 of them from Walmart. They're completely out of stock. You're going to drive over to Target, and you're going to do what? Buy a lawnmower, right? Well, how many are you going to buy? Well, most likely, if you're like me, the ultimate bargain shopper, you'll buy one of them, and you'll think, you know what, it's just eating away at me. I'm paying 10 times as much here. So you're going to drive back to Walmart and say, do you have any more in stock? No? Okay, I'll buy another one from Target. Drive back to Walmart. Do you have any more in stock? Okay, no, I'm going to buy another one. So one at a time. Essentially, you get the idea. You're only going to buy ones from Target if Walmart's completely out. And you're only going to buy them from Radio Shack if Target's completely out and Walmart's completely out. The only time you'll ever go to Lowe's is if all these guys are completely out of lawnmowers. Now with that in mind, that is exactly how priority queuing works. what happens is you're going to have 4 queues of traffic. A high queue, high priority queue, medium, normal, and low. You get to have these 4 queues and define what traffic is going to go in each one of those queues. As long as there's traffic in the high queue, it will be serviced. The medium, normal, and low will be totally neglected. Likewise, as long as there's traffic in the medium queue, normal and low totally get neglected, and these queues are the only ones that get service. So priority queuing did absolutely give us priority. However, it was almost too much priority because the traffic left in these queues could end up succumbing to the symptom of traffic starvation if you have too much traffic going through the high and medium queues. So it does give you 4 queues of flexibility, not very flexible, but typically flexible enough for most networks. It does use a strict priority method of queuing. The higher you are, the more priority you get, and these guys will never get service as long as there's traffic in the high queues. It does give you a delay guarantee for the high priority folks because they are guaranteed to get sent first, so no matter what, all other traffic will be pushed aside. It does not give you a bandwidth guarantee. You aren't guaranteed to get your bandwidth that is assigned to you. Essentially, you can't say that medium queue will get 500 kilobits per second of bandwidth, while the high priority will give you, 1,000 kilobits per second of bandwidth. You can't really allocate it that way. It's just as long as there's something in the queue, it will get bandwidth, as long as it's the high priority queue. Now, is this recommended for voice or video? I would say somewhat. A lot of the documentation will say no, because that can cause the rest of your network to fall to shambles. If you have enough voice and video calls going through that high priority queue, the rest of your network, all your data applications begin to die because they are starved out. So, recommended for voice, yeah, your voice will sound great as long as you have enough bandwidth for the voice alone, but I say somewhat recommended because if you're not careful and you have too many voice calls or video streams, the rest of your network will suffer in a huge way. So priority queuing was released and people said, wow, this is great, but it's too much. Can we find something in between, FIFO and priority queuing? And then custom queuing was born. Custom queuing is a lot like, well, donuts. Most specifically, Krispy Kreme donuts. I don't know if many of you have Krispy Kreme donuts where you live, but if you do, you know the bliss that I'm talking about. These are donuts that are coming fresh off the roller, and they're handed to you while they're still steaming. They're still hot. So what I do when I typically go to Krispy Kreme is I'll kind of create 4 little groups of donuts that I get. I'm going to go through and I'm going to get 16 glazed donuts because glazed donuts are the freshest. Those are always coming right off the rollers. I'll go ahead and get 8 chocolate-coated donuts because I'm a chocolate lover. I'll probably get, 4 of those, the ones with the pink glaze. They're kind of, I don't know, they're almost a little too sweet for me, but my wife likes pink donuts, so I get the pink donuts for her. And then I always get one of that mystery donut. You know, the one where you can kind of see the filling and you're not too sure what that filling is, so you're not feeling that brave. Well, that's why I only get one of them. And I take all these donuts back to my table and I gobble them up. I eat every single donut. And then I think, you know what? I'm still hungry. And I get back in line and do exactly the same pattern again. 16 glaze, 8 chocolate, 4 pink, and 1 mystery donut. That would kill you. However, that is exactly how custom queuing works. It works in a round-robin sense. What it's going to do is have up to 16 different queues that you are able to define what traffic is placed in each queue. So I might say, I want to put, 16, well, in this case, you would allocate how much bytes is transmitted. So we'll say 16 kilobytes or 16,000 bytes of voice will be placed in the first queue. In the second queue, you'll have maybe 8,000 bytes of HTTP. In the third queue, we'll have 4,000 bytes of FTP, and then down here in the mystery queue, we'll have 1,000 bytes of just default, whatever's left over, which could be plenty of traffic that's not getting too much service. Here's how it works. It's going to handle a round-robin system, so it will send 16,000 bytes of voice Whoosh, it's sent. Now it comes down to HTTP, 8,000 bytes, it's sent. So as it goes down, it's going to go in this round-robin sense, emptying the specific amount that you've allocated from each queue and then starting over. Now you might look at that and go, wow, that's fantastic. It gives you the ability to give you some priority, so I can send, my bulk of it will be voice and then lessen on the amount of the data side. So I'm giving some priority. But the problem is this one right here. There is no guarantee on delay at all. And when you're talking about time-sensitive applications, voice being the primary one, video and Citrix, all these time-sensitive data applications, this one is what can end up killing you. And you might say, well, I don't understand. How come this doesn't give a delay guarantee? Aren't you sending more voice than anything else? Well, yes, you can, but this round-robin mechanism ends up coming back to haunt you. The reason why is we send 16,000 bytes of voice. Great, that 16,000 will get there okay, but then what happens? The traffic cop stands right here and says, stop, you're done, cut off, I'm moving down to here. And then it sends the 8,000, sends 4,000, sends 1,000. What's happening to the voice sitting in this queue while all this is being sent? Well, you probably guessed it. It's just sitting there. Delay is accumulating. The more queues you have, you can have up to 16 of these queues. The more queues you have, the longer your voice has to wait. So by the time it does make its way all the way back around, your voice may very well be trashed at that point. It may have gone long past the delay requirements that voice needs, 150 milliseconds one-way delay, and all this voice has been delayed so long it ends up getting dropped in the long run anyway. So yes, you can guarantee bandwidth with this one. I can allocate this up almost in a percentage, so I know exactly how much bandwidth each application's getting, but I do not recommend this for anything that is a time-sensitive application because the delay can add up far too quickly. And that brings us to the final legacy queuing method called weighted fair queuing. Now this isn't really a happy compromise or anything like that between custom and priority. This is just another method that you can use. And it became so popular because it really does sound fantastic. It became so popular that Cisco said, you know what? I think we're going to make this our default queuing method for any link that is less than 2.048 megabits per second, or what they consider slow WAN connections. Now, a lot of you may recognize that speed and go, wait a sec, that's an E1 line, which is the T1 over in Europe. That's absolutely correct. So for most serial links, weighted fair queuing will be the default queuing method. Now, here's what it is. It's kind of like a meeting. I'm sure many of you have been to a meeting at some time in your life. It seems to me, at meetings, you always have one of these sort of people. These are the people that are always talking and always have their voice heard at the meeting. There's always that person that always has an opinion for just about everything. So they're always talking, or maybe they're leading the meeting and they're just they're adding a ton of conversation. So they are a high talker of that meeting. And then you have over here this person that has the paper in his hand. That's typically, believe it or not, me. Because I'm usually pretty quiet outside of my teaching role. I'm very introverted on my personality. I don't say much unless I really have something that's eating away at me that I have to say. And have you ever noticed what happens at the meetings? When there's that one person talking and everybody's kind of talking, and da-da-da, it's kind of like people start overlapping. And then you have the one person that speaks. And what happens when that person who never talks actually says something? Well, you got it. The whole table goes quiet. They're like, oh, Bob spoke. What's he going to say? They're all interested because Bob never talks. This quiet talker never speaks, so everybody waits to listen to what he says. That's what weighted fair queuing is all about. The Cisco router is able to see the high talkers of the network. These might be people like web surfers or peer-to-peer applications that are gobbling up a bunch of bandwidth. And then you have the low talkers, which might be something like Telnet. Telnet only sends one small packet at a time for each character that you press on the keyboard, aka a very small talker. So when it receives these packets and they're starting to bottle up, the queue's filling up, it's going to look at it and say, you know what? You haven't said too much, and you have a very, very small packet size, so I'm going to move you, maybe there's all these packets before it, I'm going to move you to the front of the queue. The low talkers get priority over the high bandwidth talkers. That's the concept of weighted fair queuing. The number of queues that it has is per flow. It creates a queue for every single flow that you have going through. So every single session that is occurring on your router will have its own queue. Weighted fair is the method. There's no real trick to it. It's going to be, I always think, it's just fair. The person who talks least gets heard most. So that's how I always remember that one. The problem with this one is there's no guarantee on delay. There's no guarantee on bandwidth. It's just saying if you don't talk much, you'll be prioritized. And when you think of that algorithm, do you think that would be good for voice? No. Voice and talking goes together. It's hand in hand. These IP phones, or even analog phones that are being run over the IP network, they do send a very steady stream of bandwidth. Sure, it doesn't consume too much, but it's always talking. So if you want to find a quick way to make your voice sound pretty horrible, go ahead and turn on weighted fair queuing for your voice mechanisms. It is not designed to handle the voice style of traffic. Now that you have an understanding of the legacy queuing methods, understanding the new queuing methods will be no problem at all for you. The first new queuing method that we now have that can be deployed using the modular QoS CLI is called class-based weighted fair queuing. And all it is a combination of custom queuing, a little more enhanced, let me put a big E right here, enhanced custom queuing, plus the weighted fair queuing that we had and we just spoke about, where the least talker gets the most bandwidth. Now you might say, well, how does enhanced custom queuing and weighted fair queuing go together? Well, the first thing that you're going to do is define your classes. Now that comes to a familiar term. Using our good old class maps, we can say, I want to define up to 256 different classes of traffic. Using our new enhanced custom queuing, we are able to assign specific amounts of bandwidth to each one of those classes. So I might have a class called, let's just say, standard data class. And I want to say that that class gets 20% of my interface bandwidth. That's the enhancement that we get with custom queuing. Before we had to say how many bytes of bandwidth we're able to use, and that just makes my donut analogy that much better because you're biting your donut. You have how many bytes you're able to use. Now, instead of saying bytes, because it's kind of hard to work with bytes, we can just say the percentage. We can say, I want this to get 20% of my interface bandwidth, and it will be guaranteed to get it. Now remember, this is not considered priority bandwidth, meaning it may get that bandwidth after something else, but it will be guaranteed at least 20% of the interface bandwidth. So if you have a 1 megabit per second connection, this traffic, whatever you define in that standard data class using a class map, will get 200 kilobytes of that interface bandwidth. Sooner or later, it will happen. Now, the weighted fair queuing part of this is typically used for the default class. You're going to set all of your classes up. You'll say, I've got my standard data, my high priority data, my voice, my video, all of my transactional applications. You create all these different classes of data and allocate percentages of bandwidth. You'll then finally come to your last class, which is by default named the class-default. And the things that go into the class default is, well, anything that you haven't specified specifically above it. It's kind of all the leftover traffic. That is typically queued using weighted fair queuing. So that will be used within that class default queue, where custom queuing is used for all of the traffic that you want to guarantee a specific amount of bandwidth for. So we've kind of combined two great methods together into one queuing mechanism. So the method is really a combination. There's no delay guarantee. That's one of the catches with this. We don't have priority bandwidth to give. We only have bandwidth. So it may get it first, it may get it last. There's no guarantees. You do, however, give it a bandwidth guarantee. If you say it's going to get 20%, it will get 20%. Whether it's the first or last 20%, nobody knows. Because of that, it is not recommended for voice. We can't give it priority with that priority queuing like we need for our voice, so this is great for any application except voice and video applications. So we come to the final queuing mechanism, and you might be thinking, this has to be the one for voice, right? You got it. It absolutely is the one that we're going to be using for voice. It is low latency queuing. And the funny thing is, this is a fairly new name for it. Its original name was this right here, PQ, CB, WFQ, because it really is a combination of all three queuing mechanisms put together into one algorithm. Here's how it works. We have now combined priority queuing into the mix of all the queuing methods. That will be the one that we use for our voice traffic. We can say, you know what? Voice is going to be the one that ends up in the priority queue. Now you might be thinking, well, wait a sec. If I remember correctly, priority queuing had the negative of starving out the rest of the network. How do you keep your voice traffic from causing your data applications to perform very poor? Well, they've enhanced it. They've allowed you to now set a priority queue with a bandwidth limit. Sweet. And that limit is policed, so it can never go beyond that limit. So if I say I want 500 kilobits per second for the priority queue, that 500K is all the priority queue can use. Never, ever, ever will it go above that and start encroaching on some of the bandwidth that you've allocated for all of your other applications. The donuts come back into play because we still have custom queuing. We still have the ability to say, okay, well, 500K, or maybe even, you might just say, 30% of my interface bandwidth will go towards the priority queue. And I'll say 20% of my bandwidth will go, towards the data applications, the high priority data applications. 10% will go towards email applications, which falls under data, but I'm reaching for examples here. So you can go ahead and start splitting up the rest of your bandwidth using that custom queuing style. Now remember, this is bandwidth that we're giving them, but it's not priority bandwidth. So we're essentially saying you get the first 30% of the interface bandwidth. You will just get 20% and 10%, but it will be after the first 30% is given to the priority queue. Again, weighted fair queuing falls into the same suit and gets used for the class default. Whatever you don't specify a specific requirement for ends up in that class default queue, and the weighted fair queuing mechanism is the one that people typically use for that because it's a phenomenal queuing mechanism where that low talker gets the priority over the high talker. Now, it doesn't mean you have to use it for that. For instance, I could go say, I don't want that method. I just want to use FIFO for all the other traffic. No problem there as well. It's totally up to you, totally customizable to fit your needs. So with this method, it is a combination of all three methods. It gives you delay guarantee for the priority queue traffic, whatever you specify in that queue. Now do remember, you only get one of those queues. So if you specify multiple traffic types going into that one queue, they're going to end up pretty much using FIFO within the priority queue. I'll talk about that a little bit more later. It does give a bandwidth guarantee both for the priority queue, and you can even guarantee bandwidth to your data as long as you don't oversubscribe the link. And then this is the recommended for voice and video and any time-sensitive application that needs that priority queue to give it the delay guarantee you're looking for. So now that we have these tools in hand, we come to the point of saying, how do I use them? Well, quality of service is designed around the user expectations. And it gets even bigger than that. Cisco has created the whole new AVID strategy, the architecture for voice, video, and integrated data, to allow all three of those traffic types to transparently exist on the same network. Did you catch that key word? Transparently. As in, people are running voice, video, and data on the same network, but they don't know it. They just know that everything works the way it used to. And when you're doing your quality of service, the overall goal is to make sure that your new traffic types, most likely voice and video, don't adversely affect the old traffic types. For instance, I have this guy sitting here with his coffee cup going, wow, when is my web page going to download? Or when will that email send? Or a number of things that's sitting there delayed on his screen because the company has just deployed Cisco Voice over IP and the voice bandwidth has completely eaten up all the data bandwidth. Essentially, data will scrounge for whatever's left over, but that doesn't mean that your users will like it. Overall, Cisco has done a ton of marketing, and I don't think it would take too much to figure this out. Users prefer that they get a constant, conformed data rate for their traffic. That doesn't matter if it's fast, if it's slow, just make sure it's the same. And if you give too much priority bandwidth to the voice, what's going to happen is in the slow time of days when not many people are using the phone, wow, the data is going to fly like mad. You're going to get great rates and everything like that. But as the day goes on and people start picking up the phone, calling each other, normal business happens, the data will come down to a crawl because you've provisioned too much priority bandwidth for your voice, and now nothing is left over for the data. So Cisco has come up with some rules of thumb. Not solid laws, but guidelines per se as to what you should divide up your link bandwidth with. Down here I have the total link capacity of 100%. So you have 100% of your bandwidth to play with and to use for whatever applications you may desire. They say, again, rule of thumb, you don't have to, but they say you should only allocate up to 33% of that link for your priority applications. Most likely this is going to be your voice and your video applications that are consuming plenty of bandwidth on the network. So by only allocating 33%, if the voice and the video is using that 33%, I'll just put V and V here so I don't talk and write at the same time and scramble my words. Voice and video, if they're using their 33%, you know what? We still have around 75% of that bandwidth left over for all the applications that are still using the network. So most likely people won't notice a huge difference if only 33% of the bandwidth has been taken for voice and video. Now I also, while this is fresh on my mind because I don't want to forget it, I want to talk about that priority bandwidth. When you allocate priority bandwidth with, for instance, low latency queuing mechanisms, I've gotten this question a lot because people start thinking of the theory. If you give 33% of the bandwidth to voice and video, does that mean at any time of day, say absolutely nothing is using the bandwidth on the link except voice and video, does that mean that voice and video can never, ever, ever go above 33%? The answer might surprise you, is yes, it does mean that. It means that voice and video are completely limited as to bandwidth that they can consume. Now I know your gut reaction is, well wait a sec, if the bandwidth isn't being used, why can't I allow the voice and video to use, the bandwidth left over? Why are they now limited to 33%? Well, it's because of the architecture of how this works. Imagine if we did do that. Imagine if we allocated 33%, but we said, you know what, voice and video, if you need it, you can take whatever bandwidth you need. We'll allocate 33% of priority, but you can take 50% if you really need it. Well, voice and video takes 50%, and all of a sudden it reaches a stormy time of day. Data traffic is flowing like mad. You now have two choices. One, your voice or video applications are going to be eaten alive because the data applications will destroy them if they are running in the same queues. Or that means we've over-allocated for voice and video, and now your data applications suffer. They're going to be scrounging for 50% of the bandwidth now, even though you only wanted 33% to be priority. So you can kind of see the sticky predicament that Cisco was in when they created this. They said, well, if we allow it to consume more than you've specified, what does that mean when suddenly the data traffic starts picking up? It means we have to throttle back somehow, and that means either your phone calls are going to go bad or your data traffic will go bad. So when you set this priority amount, it is a strict priority. It's known as a policed priority. It will never go above that no matter what. Now, along with that design, Cisco said that the sum of all the guarantees should only be 75% of the interface bandwidth. That means, say you use your 33% priority. Let me just do a quick math problem here on the screen. That'd be 2, 4, 42% left over for whatever else you want to allocate. So now you can use that custom queuing or the class-based weighted fair queuing mechanism to say, okay, maybe 10% of that goes to HTTP, 20% goes to FTP, and so on and so on. You'll divide it up based on your network requirements for your data, as long as you don't exceed that 75% rule. Now Cisco has even hard-coded that rule into the interface. So we'll talk about the configuration in the upcoming nugget, but when you go to apply one of these policies reserving bandwidth to an interface, if it has reserved more than 75% of the interface bandwidth, it will actually return an error message saying, sorry, you can't do that. 75% is the limit. Now what I'll show you is that you can change that limit, that upper limit of how much you can reserve, but again, it's not recommended. Now you might be thinking, well, I don't get it. It's not recommended. I mean, isn't this my bandwidth? Can't I just allocate it to whatever I want? Well, sure you can, but Cisco says that you should leave 25% for what's known as the default class. There are applications running on your network that you probably don't know about. And, you know, there's applications running even in my home I probably don't know about that are consuming some kind of bandwidth. There's applications that we can specifically allocate bandwidth for, and then there's just everything else. Cisco says you should leave at least 25% for the everything else category because there may be some application that you're not sure about that somebody needs to be using for some sort of business requirements that you didn't specifically allocate bandwidth for. That's known as the default class. So this is the best method that you should be using to divide up your bandwidth when you're provisioning your links. Well, hopefully all that design and theory behind these queuing methods got your taste buds wet for the configuration, which I'm going to be doing in the next nugget. I know it did for me. I'll tell you what, between each one of those slides and recordings, I was thinking, you know what? It would be great to do this. And wow, you know, I was thinking of all these killer demos that I could put together to demonstrate each one of these topics. But understanding the fundamentals, the design of this is critical. I mean, as a matter of fact, I have tons of books. I have a big stack just sitting to my left, all these quality of service. And I have this, I'm looking at one right now. It says End-to-End QoS Network Design by Cisco Press. And I'm looking right here. There's maybe 100, maybe 150 pages dedicated to the configuration of this. And then, let's see, how big is this book? 700 pages. Everything after that is all dedicated to the design. Because designing this is so important. You're going to see when we look at the configuration, it's not that bad. Understanding what it's going to do to your network is the part that we really need. So in this nugget, we understood the legacy queuing methods. We went through priority queuing, custom queuing, FIFO queuing, and weighted fair queuing, and looked at how we used to do all of our queuing methods back when we configured it using just the command line interface. The new, not so new methods of class-based weighted fair queuing and then the almighty low latency queuing are just combinations of these old queuing methods with new enhancements. The main enhancement that I find is that you can now configure all of these using the modular QoS CLI. Finally, we looked at the bandwidth provisioning designs, some rules of thumb that Cisco has laid out that you should reserve certain amounts of bandwidth for applications, but not over-reserve the link. Well, I hope this has been informative for you, and I'd like to thank you for viewing.